All right, this is the acid-base chart in your book here. And so here we have our conjugate pairs, acid-base, acid-base. So the acids on the left here, like our chart, the base is on the right. The only difference is they have the H plus here to show. The acids lose H plus, the bases gain H plus, going one side to the other. Now, a word about the strength. How strong is strong? Well, the strong ones are very strong here, but how weak is weak? Well, these are extremely weak. So, for example, they're so weak that we don't really consider them basic or bases. And so, like, let's take chloride for reference here. What contains chloride? Table salt contains chloride. Table salt's sodium chloride. So if sodium chloride's a base, then we could use that as an antacid. And so let's say you run out of antacid, but you have table salt. Will table salt work as a good substitute for antacid? What do you think? No, it's not. It's not going to work at all. And so that's how weak it is. Chloride is not even basic. It's pretty much neutral. And this is what makes a strong acid a strong acid. Is if chloride's seeking out H pluses, then chloride's going to try to take H pluses. But strong acids ionize or hydrolyze completely. And so they completely lose that hydrogen. Strong acids do. And the chloride isn't there scavenging for leftovers. And so in other words, strong acid, strong electrolytes ionize completely. That means chloride doesn't really have any attachment to that H plus or want that, which seeks it out. Likewise, when we get to some strong, we have more stronger bases. So when we get to strong bases like oxide, its conjugate acid is extremely weak. For example, we don't even consider hydroxide an acid. We consider hydroxide a powerful base. So it's the same token. But other than that, the relationship works. The stronger the acid, the weaker its base. We'll be using this chart. So list the following acids in order of decreasing strength. So which of these acids is strongest? This one's called the hydrogen oxalate ion. Oxalate is C2O42 minus, and then we throw an H plus, so hydrogen oxalate. This is ammonium. This is phosphoric acid. Just take a guess. Which would you guess is the strongest? Go for a guess. What's that?
Phosphoric acid.
Phosphoric acid, you're right. Phosphoric acid is the strongest. Which is next? Maybe that's more difficult. And so what we'll do is we'll just look at the chart table. And so here's phosphoric acid. Here. Here's a hydrogen oxalate here. And here's ammonium here. So it'll go phosphoric acid to hydrogen oxalate down to ammonium. Ammonium's a pretty weak acid, but it's still better than water. So we could use the chart to determine that. That's what they expected to do. All right, next we're going to look at predicting reactions. Basically, what we want to do is we want to go from, this is kind of confusing, this chart is, but this chart is based on our thing. We want to go from stronger acid, stronger base, to weaker acid, weaker base. And so it's always going to occur this way. It's always going to be strong, strong, weak, weak, or weak, weak, strong, strong. It's not going to be strong, weak, strong, weak. It's not going to interchange like that. Okay. Okay, so we're going to come back to this chart later, but we want to go from strong to weak, strong to weak. On the chart, on the acid side, the acid side's on the left, we want to go down on the acid side. That's favorable. On the base side on the chart is inverted, so we want to go up on the base. So if we go down on the acid side and up on the base side, we're good. Does that make sense? But this chart we're going to look at in a little bit more detail later. And so what we're going to do is we're going to try to predict some reactions. Hydrofluoric acid and sulfite ion. So this is not a complete thing. This is kind of a mix of net ionic, whatnot, but net ionic, complete, and whatever. So we aren't just going to have a ball of sulfite ions. We have to have some other spectator ions present to neutralize that charge. But what's the formula for hydrofluoric acid? Do you guys remember? What? Do you guys remember? Hydroic means what? Yeah, fluoride, which means HF. So hydrofluoric acid. Sorry. Sulfite. One less oxygen than sulfate. What is sulfate? SO4 charge?
Minus. 2 minus.
So sulfite would be SO3 minus. All right, then we do this. Since we're learning about acids and bases, we go to the chart next. And then we look for HF on the chart. The first thing is HF. Well, HF is here, weak acid. Then we look over here. Does HF occur over here? No. So HF, the only thing it can be is an acid. And so what I'm going to do is I'm going to label it A for acid. Then we look for sulfite. So I'll scan down the left, there's no sulfite. Then I'll look on the right, there is sulfite. It's right here. You see that? So sulfite is our base. And so what happens is the acid loses an H+, the base gains an H+, and so what are the products of this? Well, HF loses an H+. So if HF loses an H+, we form F-. And SO3 2- gains an H+. If it gains an H+, we form HSO3 charge, not 2-, -1, because H+ is positive, so we knock out one negative charge. Now, HSO3 is a bit tricky because HSO3 occurs on both sides. Do you see HSO3s here? And then up there, can you see HSO3 near the top?
Yeah.
So HSO3 occurs on the acid side and the base side. But how it reacts depends on what we react it with. HSO3 is what we call amphoteric. And so what we do is it doesn't matter where it occurs on the chart. We use the reaction to figure it out. So if we go backwards here, which one loses the hydrogen, which one gains the hydrogen? Yeah, the hydrogen sulfide ion is the acid and the base would be fluoride. And so this is going to happen a lot because what happens, we got a lot of amphoteric species that occur on both sides, and you don't know, is it the acid or is it the base? You have to look at the reaction. When you look at the reaction, you look who loses, who gains. Or you look who's the strongest. You know, the strongest acid will gain, the strongest base. I mean, the strongest acid will lose and the strongest base will gain. All right, the next step is we just look, which way is downhill? And so what we'll do is we'll compare the two acids, HF versus HSO3 minus. So HF versus HSO3 minus. Which one's stronger? HF. So we're going from stronger acid to weaker acid. All right, so that's downhill. Now what we have to do is we have to flip upside down because the bases are going to go in the opposite direction. And so if we look at sulfite versus HSO3 minus, well, here's sulfite, here's HSO3 minus. Which one is a stronger base, sulfite or HSO3 minus? Sulfite. The strongest base is on the bottom here, so we've got to go this way. This way is, what I mean by downhill is energetically, not in that chart. And so sulfite is a stronger base, fluoride is a weaker base. And so this is what we call driving force here. Stronger acid, stronger base to weaker acid, weaker base. So we have that here. We haven't gotten to redox reactions yet, so I'm not going to talk about redox reactions right now. But there's similarities, some similarities. Redox reactions in the next chapter. We'll talk about those when we get there. So, let's try another example here before we move on. When we look at this reaction here, sodium bisulfate plus sodium bicarbonate, it looks like a double replacement reaction. But if you do it, if you switch it, you know, here we have the sodium cation with bisulfate anion, here we have the sodium cation with bicarbonate. So we switch the ions, what do we end up with? We end up with the same thing. You know? And so there's no reaction in metathesis here. But let's take a look at acid-base. For acid-base, what we do is we inventory the solution first. And so step one, inventory. What I mean by inventory is we just figure out all the species, the major species in solution. So in sodium bisulfate, that's going to consist of sodium ions and bisulfate ions. For sodium bicarbonate, we're going to get sodium ions and bicarbonate ions. Okay, the next step is we identify the acids and bases. So, 2, ID, acids and bases. So sodium ions, are those acids or bases or neutral? Are sodium ions hydrogen donors? No. Are they hydrogen acceptors? No, they don't want them. Sodium ions aren't going to be on your acid-base chart, so we're going to call that neutral. Neither an acid nor a base. It's neutral. Now, how about bisulfate ions? So when we go back to this chart, sodium ions aren't going to be on this chart here. And so next thing, we look for bisulfate. You see it here? I see bisulfate here. It's on the left side, so that means bisulfate is a acid. But I need to look at this chart once in a while because not only is bisulfate on the left side here, it's also on the right side. There, do you see it up there? And so bisulfate is both an acid and a base. Sodium ions are neutral. What about bicarbonate? Let's take a look for bicarbonate. Let's see, bicarbonate. Let's scroll down a little more. Oh, there it is. So I see bicarbonate on the left side, that's an acid. So bicarbonate's an acid. And do I see it on the right side? Yeah, it's also a base. When something can act either way, as an acid or a base, we call it amphoteric. You know, the most common amphoteric species is water. Water can go either way. Is water present in this reaction? Yeah, because these are AQ. And so we also have to consider water. Since these are aqueous species, there's plenty of water around, and water can act also as an acid and a base. And so let's look for water here. You see water on the left side? Right at the bottom here. It's easy to ignore because it's so weak. Do you see water on the right side? Up here. It's easy to ignore because it's so weak. But weakness and strength is a relative thing. So we could be reacting with something even weaker. It's always possible. All right, 3. Choose the strongest acid. And strongest base. All right, so I have 3 acids. Which of those 3 acids is the strongest? We look at the chart. So it's going to be HSO4 minus versus HCO3 minus versus H2O. So let's find these on the chart here. So HSO4 minus is here. Where's HCO3 minus? Yeah, it's way down there. HCO3 minus is here. Where's H2O? Even farther down. So out of these 3, which one's the strongest? Well, HSO4 minus. So let me circle that one here. It's our strongest acid. Which one is our strongest base? Okay, yeah, we can just go down. We have 3 potential bases, and then we look at which one is the strongest. The strongest base is at the bottom. So let's scroll up here. And there's HCl3 minus here. And what else? HSO4 minus is up here, and H2O is here. So HCl3 minus is the strongest base present. So that's 3. Step 4 is we're going to react the strongest acid with the strongest base. Step 4, react by transferring H plus transfer, proton transfer we call it. Proton transfer. So what we're going to get is this, HSO4 minus plus HCO3 minus. Who loses the proton?
The acid.
Well, which one's the acid? HSO4 minus. So this is the acid, this is the base. So what do we form? H2CO3 and
SO4 minus.
yeah, SO4 2 minus plus H2CO3. We know that. Is H2CO3 stable? No. It should decompose. H2CO3 should decompose into H2O liquid plus CO2 gas. In this chart, they don't decompose it. In the other chart I showed you, they do. Here, they have H2CO3. Okay, so we did that. Step 5 is determine driving force. So in order to determine driving force, we have to figure out which way is downhill. In other words, we have to reverse this reaction and determine if we go backwards, who's the acid, who's the base. The way we determine that is who gains the proton, who loses the proton. So who loses the H? H2CO3 loses the H. Who gains the H? Sulfide. So this is the base. The acid loses, the base gains. Okay, then we compare. What are the two acids we're going to compare? We're going to compare bisulfate versus carbonic. Which one's stronger? Here's carbonic or bisulfate. Which one's stronger? Bisulfate. And so this is stronger acid to weaker acid. Therefore, it's downhill in the forward direction. Likewise, the bases have to follow, but the bases are inverted. So which base is stronger? It's also the conjugate relationship as well. But if we look at bicarbonate here, is stronger than sulfate. Sulfate's up here. So bicarbonate is stronger than sulfate. It's weaker. So strong, strong, weak, weak. This is driving force. This is downhill. So we expect a reaction to occur here to form carbonic acid. So on the left side, we went down. That's favorable. So going down on the left side is favorable, and going up on the right side is favorable. So this is what they mean. Going down on the left side is favorable, and going up on the right side is. And so that's driving force here. Particular reaction. There's one more way to use this chart, and that is this. The other way to use this chart is HF. What bases will HF react with? Well, will HF react with this base, H2PO4 minus? Well, if HF reacts with H2PO4 minus, then HF loses, H2PO4 minus gains. And so this is what happens. HF donates a proton to H2PO4 minus to form H3PO4. Is that favorable? No, it's not favorable because we're going uphill. Do you see that? Whereas is HF, will it react with nitrite? Well, if HF reacts with nitrite, then HF donates a proton, nitrite gains a proton to form HNO2, nitrous acid. Is that favorable?
Yes.
Yes, that's favorable. And so we could do a quick thing here. We could use this chart to figure out all the bases HF will react with. HF will react with any base that's stronger than fluoride, so it reacts with everything down here. So let's take another example. HF will react with HS minus. If HF reacts with HS minus, so we go HF to HS minus, what forms? H2S. Well, that's stronger to weaker. That's favorable. Do you see that? And so HF reacts with any base stronger than fluoride. about HCN? HCN will react with any,
Oh. Any base lower than CN, right?
yes. That would be downhill because like for example, HCN will react with carbonate to form bicarbonate. Well, we're going from stronger acid to weaker acid. But will HCN react with ammonia? No, because we're going to go, HCN reacts with ammonia, we're going to form ammonium, which is stronger. So we're going from weaker to stronger. That's unfavorable. And so in this way, we could rapidly see everything that reacts with. So for example, if I asked you for acetic acid, HC2H3O2, will it react with fluoride? Will acetic acid react with fluoride? The answer is no, because if acetic acid reacts with fluoride, we form HF. HF is a stronger acid. Will acetic acid react with sulfite? Yes. Yes. React with sulfite. And so this is the pattern here. We want this to react so that we go down. We don't want this to react up here to go up. So this is kind of the pattern that they're trying to show on this slide. Let's do one more example here. I'm going to put some sodium sulfide into sodium chloride salt solution. What happens here? Can you tell me what happens? Do we expect a metathesis reaction to occur? No. If there's no metathesis, we might start looking for acid base. So what are the steps? Step 1. Inventory. So sodium sulfide is going to consist of sodium ions and sulfide ions. Sodium chloride consists of sodium ions and chloride ions. This is aqueous, which means what else is present?
Water.
Water. And water is amphoteric, one of the most common amphoteric species we do. Okay, what's the next step?
ID acid bases.
Yeah, so we'll need the chart to do that. This is the wrong chart. This chart's from old data. Let me use my chart. Okay, I have to zoom out here to get it all of that. Okay, let's see here. Sodium ions, acid, base, or neutral? Sulfide.
Strong base.
Yeah, sulfide's a strong base. Could it also be an acid? No, there's no H. This is just a base. Sodium ions, neutral. Chloride, very weak base, so weak it's almost neutral, right? And so base, we'll just put that in quotation. Water,
Acid base.
acid base. And so when we look at this reaction, there's only one acid. But there are two bases. So which one's the stronger base? It's the sulfide. And the strongest acid present? Water. So the reaction isn't between these two. The reaction's between this and water. And so the reaction is sulfide, which is our base, reacts with water, which is our acid. What forms? Yeah, hydroxide's one of the products. What's the other product? HS minus. That's correct. Then, in order to figure out which way is downhill, we're going to reverse it. And so going backwards, which one gains, which one loses?
Sulfur gain.
Okay, going backwards, does HS minus lose or gain? Lose. If it loses, it's the acid. Hydroxide gains. That's our base. Okay, then we look at the chart and tell me, do we have driving force? So, take a look at the chart over here. Which one's a stronger acid? H2O or HS minus? H2O. So we're going from stronger acid to weaker acid. Which base is stronger, sulfide or hydroxide? Sulfide's stronger. So it's going strong, strong to weak, weak. This is our driving force here. And so there is a reaction. The reaction is going to be between the sulfide from sodium sulfide and water. So the reaction is not between sodium sulfide and sodium chloride. The reaction is between sodium sulfide and water. That's a tricky question. Well, okay, I gotta wrap it up now, so that's all we have time for.